Okay, so in this video, we will consider an example of goodness of fit. So before we consider this example, let me give you a brief introduction to the idea. If you remember so far in this course, several times we said in a problem, let's assume that a population follows a Poisson distribution or a normal distribution. And the question is, well, how can we justify making such claims? If we have a random variable, how do we determine which distribution it follows? And the idea is goodness of fit. So what we'll see, and this will be really closely related to test of independence as far as the statistic is concerned, we will consider a random variable, and we are going to ask what distribution does the random variable follow? Now if you think of how you would first come up with a heuristic guess, well, if you think of it, you would take a fairly large sample of values of this random variable. Then you would organize the values into bins. And then, as we saw early on in the course, you would produce the histogram of the distribution of the random variable. And when you look at the histogram, that's when you can graphically, visually see if the histogram, your distribution, looks like maybe a binomial, a Poisson, a t-distribution, a z-distribution, or a chi-square, or any other well-known distribution. But then, how do you give more weight to your guess? Suppose that you look at your histogram and you say, the histogram looks like a Poisson random variable, or a binomial. How do you go a step further into giving more support to your statement? And the idea is goodness of fit. Let's read the problem, and you'll see that what we will do in this problem will be the same for any other type of distribution. So we have a call center was monitored for 160 hours, and the number of calls per hour was recorded in the following table. And so you see our random variable here is over a fixed time interval of 1 hour, how many calls were received at this call center. And so you see here we have a random variable, the number of calls received per hour, and then we have our bins. The first category is maybe we received no call during 1 hour, maybe we received one, maybe it was two, maybe it was three calls in the given hour, or maybe our last category is more than 3 calls per hour. So maybe 4 or 5 or 6 or beyond. And you'll see very shortly why we stopped at 3. And now we have the observed frequency. So we observed over 160 hours, 160 1 hour time intervals. So we have 160 observations, 53 times. So for 53 intervals of 1 hour, we observed 0 calls. For 62 1 hour intervals, we observed 1 call. For 33 1 hour intervals, we observed 2 calls. For 12 1 hour intervals, we observed 3 calls. And we never observed more than 3 calls per hour. So here's the claim. So of course, before making this claim, you would then produce the histogram of this distribution. So over the interval 0, or the bin 0, you'd have a bar where the proportion is 53 out of 160. Over the bin 1, it would be 62 out of 160, and so forth. And then you may look and say, this looks like a Poisson distribution. And so you say, well, okay, how do I test this claim? And we'll see how, and this is the problem. We want to test the claim that the number of calls per hour, a random variable, follows a Poisson distribution with a mean of 1 call per hour. Oh, and this one, there's something missing, sorry, here, right? We're considering the number of calls per hour, so here with a mean of 1 call per hour. because again we're considering the random variable that is the number of calls per hour. So the mean should be for the number of calls per hour. So before we look at our hypotheses and then test whether or not we accept this claim, let's just quickly go over the statistic. As in the case of a test of independence, we will use uppercase N for the number of observations. Here we observed 160 1-hour intervals, so that's the number of observations. And if you add those up, you will get 160. We have 1, 2, 3, 4, 5 categories, 5 bins. We use lowercase n for that. And as always, under the assumption of h naught, what we have here were the observed values for each bin. We will compute under h naught expected values for each bin. So this would be O1, the observed value, the first observed value. This would be O2, the second observed value, O3, O4, and O5. Under h naught, we will compute E1, E2, E3, E4, E5, the expected values. And if you ask, well, what is our statistic? It is basically the same as in the case of a test of independence. We will sum over every bin. So since we only have a single row, we only have one index, and we will sum the difference between each observed value and its corresponding expected value squared over the expected value. This will follow approximately as long as in each bin each expected value is above 5. This will follow approximately a chi-squared distribution with n minus 1 degrees of freedom. So the f will equal n minus 1. So this is the general statistic in the case of a goodness of fit, trying to fit a random variable to a distribution. Or I should say fit a distribution to a random variable. So now we're good to go. We have our statistic. And again, we will have a right-tail test. Because under h naught, we will obtain these expected values. And so if h naught really is true, then e should be very close to O. So this should be a very small number. So on average, you will be adding small numbers, and so you should get a small value of chi-squared. So a small chi-squared value will support h naught. A large value of chi-squared will go against h naught, and so that's why we only reject the right tail of our distribution. Here we are using a 5% level of significance, so alpha is 0.05. Let us now state our two hypotheses. We will, as always, be under the assumption of h naught and formulate h1. Well, what is the claim here? The claim is that the number of calls per hour, we could call that x. This is our random variable. The number of calls received at this call center every hour. And the claim is that it does follow a Poisson distribution with a mean of 1 call per hour. So if you remember, the only parameter for a Poisson that is required is the mean. And again, this is lambda equals 1. Now what is h1? Well, it's simply the negation of this. Either x follows a Poisson distribution with a mean of 1, or it doesn't. And we simply write x Poisson. And if you remember, this means that x follows this distribution. If you want to say x does not follow this distribution, you simply put a slash across this symbol. And that is h1. Now there could be two reasons why this could be the case. Maybe x does not follow a Poisson distribution, or maybe x does follow a Poisson distribution, but maybe the mean is actually incorrect. So there are two possible reasons why this may actually not be correct. The distribution could be wrong, or the mean could be wrong. The only question we have now is how do we compute, under the assumption of h naught, the expected value for each of our 5 bins? Well, if you think of it, under h naught we have a distribution. So we assume that x follows a Poisson distribution with a mean of 1 call per hour. And so we can find the expected value for each bin using the Poisson distribution. If you think of it, you see, well, out of these total number of n observations, what is the proportion that will fall into every given bin? So this is bin 1, 2, 3, 4, 5. And the idea is quite simple. It simply is the probability that the variable falls inside that bin times the total sample size, because again, a probability is simply a proportion. So if you multiply the total sample size by the proportion of values that should fall inside of the ith bin, you will get the expected number of values inside of that bin. So all we need are the values of E1, E2, E3, E4, and E5. Then we will find our observed value of chi-squared, and with the help of the rejection region, decide if we accept or reject h0. So let's compute these 5 values. So E1 equals E2 equals E3, E4, and E5. Well, what is the probability? Let's remember the distribution for a Poisson random variable. If you ask what's the probability that x equals a given value, if you remember, it is e to the minus lambda, where lambda is the mean, times lambda to the x over x factorial. But here, since the mean is 1, we will get e to the negative 1. Now 1 to the x, 1 to any power is simply 1 over x factorial. So it will be e to the negative 1 over x factorial. So because the mean is 1, it gives us a slightly simpler expression. So now let's go. E1, well, what is bin 1? It is the category that x equals 0. So we need the probability that x equals 0 times the sample size, and we had a total of 160 observations. So times 160. What is E2? Well, the bin for E2 is this one, and this is x equals 1. The number of calls per hour equals 1. So that's the probability that the number of calls per hour equals 1, times, as always, the total sample size, 160. Then we'll keep going for the other 3 very quickly, because bin 3 is x equals 2, bin 4 is x equals 3, and for this one, you'll see that there's a very easy shortcut. So p of x equals 2 times 160, p of x equals 3 times 160, and we'll wait till the end to compute the expected value of the last bin, where it was x was greater than 3. Well, in each case, we will get e to the negative 1 over x factorial. So this would be e to the negative 1 over 0 factorial. E to the negative 1 always over 1, 2, 3 factorial times the total number of observations, so times 160. And if you evaluate all of these numbers, you'll find that the first is approximately 58.86. The second is the same, roughly 58.86. 28.86. Then we get roughly 29.43. Then we get roughly 9.81. And now if you think of it, how do we get the last expected value of our last bin? Well, it's quite simple. We have a total number of 160 observations. So all of these must add up to, including E5, 160. So all we do is we do 160 minus all of these values. And if you do so 160 minus E1 minus E2 minus E3 minus E4, you will find approximately a value of 3.04. And if you look at a requirement that to have a good enough approximation, that each expected value had to be at least 5, well, if you look here, we're okay. The first 4 are way above 5, and the last one is close enough. And that's not such a big deal. As long as the bulk of your values are above 5, you will have a close enough approximation. So now we can compute our observed value of chi-squared. Let me just remind you of what were the actual observed values in each case. If you just go up, they were 53, 62, 33, 12, and 0. So those were the observed values. Those are now the expected values. And now we can easily compute our observed value of chi-squared. So our chi-squared observed is, well, we are summing, if you just look up, the observed value minus the expected value squared over the expected value. So the first one is 53 minus 58.86 squared over, and of course, the expected value, 58.86, plus, now we add these for every term. So this one minus this one squared over this one, the same for these two, and then finally, let me write the last term, the observed value 0 minus the expected 1, 3.04, squared over the expected value 3.04. And if you compute this, you will find an approximate value of 4.71. Of course, the only question is, how big is this relative to our significance level? So to decide if we accept or reject H0, we have to construct our rejection region. Remember that we have a chi-squared distribution. Since we had 5 bins, 1, 2, 3, 4, 5 categories, the degrees of freedom in our case is actually 5 minus 1, which is simply 4. So with 4 degrees of freedom and 5% level of significance, we can now construct our rejection region. We have our chi-squared distribution. And again, we have a right-tail test because the values of E were given under the assumption of H0, that our random variable x does follow a Poisson distribution with a mean of 1 call per hour. And so if we have a large chi-squared value, it means that O and E are far apart. And so the predicted values under H0 are actually far from the actual observed values, and that is of course evidence against H0. And that is why we reject the larger chi-squared values. In our case, we chose to have a significance level of 5%, and we had 4 degrees of freedom. If you use your table of the chi-squared distribution, you find a corresponding chi-squared value of 9.49, sorry, 9.49. And so we have our rejection region. 9.49 all the way up to positive infinity. Well, recall that our chi-squared, our observed chi-squared value, was approximately 4.71. And clearly 4.71 is less than 9.49, and so our observed value does not belong to the rejection region. So this is small enough. Therefore, on average, the observed values and the predicted values on the H0 are close together. Therefore, this supports H0, and so we accept H0. So we accept the claim that if X is the number of calls per hour received at this call center, that X does follow a Poisson distribution with the mean of 1 call per hour. And that's it. The only difference when you try to fit a different distribution to a random variable will be how you find the probability for every given bin. Here we use the formula for the Poisson distribution because under H0 we had a Poisson distribution. If you were assuming a normal distribution under H0, you will find probabilities for each bin using the normal distribution, and so on.